eyes on you. Felt everything around me move. Got nervous when you looked my way, but you knew all the words to say. Then your light slowly moved right in. All the time, my love, where you been? Amore, don't you know? My love, I want you so. Sugar, you make my soul complete. Rapture tastes so
All right. All right. I guess audio is good. All right. Good afternoon, everyone. Welcome to our panel session today. So we will be talking about anything and everything 3D IC. So the topic is top 3D IC innovators tackle multi-physics challenges in multi-die silicon design. And we have a really amazing group of panelists. So my name is Murat Becer. I am head of R&D for Ansys Semiconductor Products. And where's my clicker? Okay, let's see.
Uh-oh.
There is a slide clicker not working.
Tech support.
Press harder. Maybe? All right, you guys are working on this? Okay, there we go.
Okay, there you go.
All right.
Oh.
Yeah, thank you. Okay, now let's go around the arc, I guess. Introduce other panelists.
My name is Sonia Leon. I'm a senior principal engineer and director of system design technology at Intel Foundry. I drive the design technology optimization for the definition of the new 3D IC platforms at Intel, including silicon and packaging technologies, the development of design methodology to optimize across the product stack, optimization with EDA features, the technology, and the product user scenarios. In my team, we build the reference designs and the product-like prototypes for the certification test chips. I come more from the product side, so I have been at Intel 15 years. I was in the modem team and the mobile group. Before that, I was at Sun Microsystems doing servers. I did 4 years in SoC, all-in-one PC. And before that, I started my career over 3 decades ago doing DSP chips for cellular with 1 micron technology.
All right, thank you, Sonia.
Hi, my name is Prakhar Mathur. I work in developer relations, EDA developer relations at NVIDIA. This is a new role for me. How do I fit into this talk is because I've spent 22 years previously at NVIDIA building chips. I've led large teams and large chips to tape out. I've also led initiatives where we explored 3D IC topics and helped create the roadmap that we are working on right now. So a lot of chip background, a lot of like a user for 3D IC technology. Not really, it's like a complementary role that panelists here are doing.
Thank you, Prakhar. Nitin?
So my name is Nitin. I am the methodology lead for 3D IC and multi-die products at Marvell. Before that, I did about almost 20 years between AMD and Xilinx. Most recently doing 3D IC stuff, but generally, as far as CAD and methodology went, I was always bouncing between EMIR, STA, ESD, thermal stuff. I did some net listing. I did some IP integration, some flow infrastructure. So I've managed teams. I've been a technical lead. So I've done kind of bounced around everywhere within the industry and within those two companies. So yeah, most recently 3D IC, but really done a little bit of everything over the years.
Thank you, Nitin. And Lluis.
Hi, my name is Lluis, Lluis Paris, Lluis in Catalan. I work in TSMC. I'm responsible for the IP ecosystem. and the advanced packaging ecosystem that we call 3D Fabric. This is a very interesting time for the advanced packaging, all this new activity coming, the new methodologies, trying to handle the growth, this very active growth, about mostly AI-driven advanced packaging for TSMC. Before that, I've done a number of other things. Mostly 15 years ago, I had an IP startup that TSMC bought in Canada, and that's how I joined TSMC.
All right, thank you, Lluis. Thank you, everyone. So we really have a great representation of the ecosystem here. So the way that this is going to go today is, so I'll present 5 or 6 very short slides to kind of frame the topic and what we're going to be talking about. Then we'll go into a discussion, very informal discussion, some questions, and let's see how it goes. Then, we didn't really plan for time, but hopefully at the end there will be some time for questions as well. We'll make sure we'll end at the right time. Okay, so 3D IC. So what I'm sure everybody knows what 3D IC is, but just to frame the subject. So here the picture on the upper left, right? What you see, that's a very simple cartoon picture of one of the most complex 3D IC designs today that is in production, kind of an AI accelerator type design, right? You have a package, you have interposer, you have a HBM memory stack with a base die, and you have some compute chip, CPU, GPU, and very high speed digital connection between these pieces. A lot of TSVs and microbumps, and going forward, if you look at the right-hand side, upper right-hand side, that's courtesy of TSMC from ISSCC conference last year. Now we're bringing in photonic chip into the same package. Interposer is getting more and more complex. There's integrated voltage regulators within the interposer, and the whole thing is becoming many X factors of the reticle size. So overall complexity is increasing as we go forward. And at the bottom, as you can see, it's a very heterogeneous problem or heterogeneous challenge, right? You have very heterogeneous structures. You have analog mixed signal chiplets or components. You have RF components. You have digital chiplets. You have photonic IC. All of these under a single package. It's a very heterogeneous process environment. You can have these multiple chiplets can be in different processes, different nodes. Various materials are in use, and also it's an ecosystem challenge. Right? Different vendors are providing different parts of this system. So why are we dealing with all this complexity? Because there are huge benefits, right? If you look at the size and the integration density, right, we're really able to put in more functionality under a single package. Power and performance, there are many benefits. Higher bandwidth, lower power, lower latency, right? These are exactly the things that we need to enable, high performance compute, AI type applications. Flexibility with, different chiplets can be in different process nodes at different maturities. So various semiconductor companies can focus on their differentiation, maybe on a particular chiplet, and bring the other chiplets from outside. Right? So that kind of flexibility is coming in. So again, with smaller pieces, yield is likely to be better. And you can integrate these heterogeneous components closer together, right? So the whole thing can operate lower power and faster. And of course, this is not new, right? We're not just talking about 3D IC as something new. We have been innovating and seeing products in the market the last several years. These are some examples, mostly around high performance compute, AI type applications. But as you can see on the lower left-hand side, there's also image sensors, and other applications are also emerging. And as ANSYS, we have been at the leadership of all of this effort with all foundries and semiconductor companies for several years. We have about 175 3D IC. And when I say 3D IC, I mean 2.5D, 3D, right? All different combinations. Tape out. So we have a very comprehensive and mature workflow that addresses all the challenges that we will be discussing today. So it's a very multi-physics challenge. As you can see here on the left-hand side, it's power integrity, and these very high-powered chiplets, very close together under a single package. They create heat, so it's thermal integrity. This heat can create mechanical, structural type challenges. So it's a structural integrity. Signal through the interposer, very high-speed signals. So it's a signal integrity. ESD, again, right, through these multiple chiplets, interposer, a lot of new ESD paths that need to be looked at. So it's a ESD integrity. So very challenging multi-physics problem. It's a multi-scale problem also, right, starting from the transistor level to analog mixed signal, right, to your IP, to digital blocks, everything coming together in a chiplet, these multiple chiplets on the interposer and the package and the board. So starting from the nanometer scale all the way up to centimeter scale, so it's a multi-scale problem. Design stage also, right, it's not just a sign-off problem, but it's really, you need to start looking at it from early on to sign-off, so it's a multi-design stage problem. Also, it's a multi-vendor challenge, as we discussed, with multiple vendors working on different pieces. Of course, foundries and OSATs come into the picture also to complete the ecosystem, multiple materials. So many challenges that we will be discussing today in the panel. So as I mentioned, if you look at the overall design process, starting to look at this very early on during feasibility, prototyping, because the overall optimization space, the exploration space, the design space is so huge, and you need to converge on a very small minimum that is your optimal for all the power and thermal and signal and structural, right, all the integrity, all the reliability problems that you need to solve. So starting early, feasibility, prototyping, design space exploration, then in-design awareness of all of these multi-physics effects. Then of course, sign-off, right, very accurate, golden sign-off. And of course, post-manufacturing, silicon life cycle type applications also. So it's a complete, design cycle needs to be aware of, multi-physics, and so that we can address all of these challenges across all phases of the design cycle. So I'm not going to talk about in detail, right, the ANSYS solutions. We have, as I mentioned, we have a comprehensive portfolio that addresses all pieces of the problem. So this is one example here with Red IC Electrothermal, which is our multi-physics platform for 3D IC multi-physics analysis. But what I would like to say is, and this is the last slide, is that in this design automation conference, we had 43 papers that were submitted and accepted and presented in the yesterday and today and tomorrow, talking about how our customers, right, the semiconductor industry, are solving their most difficult challenges using ANSYS solutions. And several of these were on this topic, on 3D IC. So if you missed those, please reach out. We can point you to those presentations and papers. So with that, that was my last slide. So we will get into our discussion. And so let's start with the challenges. Right? So I talked about some of the challenges. So I'd like to ask each of you to talk about, in your mind, right, what is the top, or what are the top challenges about 3D IC? So maybe we start with you, Sonia.
So for me, 3D IC, in order to really fully take advantage of the technology, it requires a full optimization across the entire product stack, all the way from the software, the architecture, the workloads, to the microarchitecture, to the design, foundation, IP, methodology, down to the transistors, right, and the packaging. So it needs a bottoms up and a top down. We saw how in the monolithic die with DTCO, we were able to get half of technology node by optimizing IPs, process, and the EDA. But now we're getting like kind of design optimization in steroids, right? We're bringing the packaging together with giving the designers another knob in order to fully optimize to the system level. So even when we do technology definition, in the past, the packaging guys and the silicon guys didn't talk to each other, right? Mm-hmm. Now, what we learned is that when we put a platform together, a technology, it needs to be defined together. silicon and packaging as one single holistic solution, and from the design and product perspective. If you don't have in mind the design use modes in order to do the design technology analysis, if this feature in package and silicon is not good enough, you just have good technology for papers and patents. So at the end, what it translates to the product level? The technologists need to understand what are the use modes. The architects need to understand how to use the technology. If the, let's say, foundation IP, if the memories are not optimized to take advantage, let's say, of hybrid bonding going vertical, and you're trying to just place and route your 2D, you're not going to get the best out of the technology. So to me, it requires, it's also a mindset change, because people are used to think about, this is, I'm an expert. Well, now you need to work as a team, right? And co-optimize everything from silicon, packaging, technology, software, hardware, design methodology, ideate, everything. So it's a different mindset of putting all the pieces together. To me, that's the biggest challenge, because everybody is used to, let me take care, I joke sometimes like, everybody's holding one leg of the chair, while you are trying to furnish the entire house in a holistic way.
Yeah, bringing in different themes, bringing in different pieces,
Right.
so the whole workflow works. Yeah, thank you.
Yeah, so the challenge and the opportunity, it's not just a challenge, it's also an opportunity is to create systems which are unique, which were not possible 5 years ago. Because not only can we integrate multiple chiplets together, we can, that allows us to have multiple Lego types playing blocks where we can create unique products out of the system. The challenge from the side is when we start project planning in the past, if you go 10, 15 years ago, you could design and plan your chip. Now, chip planning is not sufficient. It's a product planning which includes packaging, which includes other IPs which are not just on the die IP. It could be a chiplet IP. You have to pull in the thermal team. Thermal is not just what's happening on the chip. What's happening on the neighboring chip is also extremely important. You need to have mechanical issues which you have to deal with, because you're dealing with warpage, you're dealing with packaging processes which could impact your mechanical bonding. So all of these issues are to be planned even before you start laying down or you start doing place and route, because you cannot just start placing route and say, my chip is ready, but what's it going to do on its own, because you can't have your other neighboring chiplets in there. Opportunity is great. It just does unlock a lot of new things which were not possible. But as every opportunity, it comes with lots of challenges that you have to solve as a team.
Yeah. Thank you.
Yeah, the thermal one is always the one that jumps out to me. You mentioned thermal. Thermal scares me a lot, because when you're stacking these dies, we have to figure out ways, we have to talk to our partners, talk to our foundry partners, figure out ways for evacuating that heat out of the system. For me as a CAD person, I also think about sign-off analysis. I think about these, if I'm trying to sign off just one die, whether it's STA, EMIR, ESD thermal, any kind of sign-off, just signing off one chip by itself is already huge. We're already talking about a data footprint that is potentially terabytes of memory in my compute farm, that is terabytes of disk space on my disk and my storage. We're talking about hundreds of cores to compute to do all this distributed analysis that obviously we're hearing more and more about today. And it's really not the sort of thing that fits in our machines, in our farms. And that forces us to start to look at abstraction models. We have to look at different types of modeling, different types of data reduction. And when you start to go down this road of data reduction, now you're starting to introduce error. So now you need to understand, what kind of error am I introducing into my system? How am I thinking about that? How am I adjusting for that, working around the error, making it more, trying to resolve those potential accuracy problems that I'm introducing? Of course, thermal is its own big problem. And the other one, I think we've already covered this a couple times, is communication. And for us, it's funny, because for us as engineers, we go to school, we learn all of the technical details of what we're doing. The one thing we don't necessarily learn is how to talk to each other, how to communicate, how to disagree respectfully, right? So for us as engineers, like we're saying, it's not just about thinking about, okay, give me the spec for my piece. I'm going to go off into my cave and design my piece to spec, and then I'm not going to talk to anybody. I'll deliver it in a couple months, and my part will be done, and I'm scot-free. we have to be talking to each other, we have to be having a holistic system level communication, and that could mean design leads from each team, design leads for the full chip, package leads, maybe even software leads, coming together to understand not only what is my piece doing, but how is my piece impacting the bigger picture? Am I creating heat that is affecting the die next to me? Am I absorbing too much power that is creating an IR choke point? All these sorts of questions are potentially impacting not just us, but the world around us within this 3D system, this holistic system. And we have to make sure that we're talking to those around us, and we are establishing this whole ecosystem of everyone talking to each other and understanding, is the whole system going to work?
Yeah, thank you.
Yeah, and from our side, from the foundry, we feel it's early, and because it's early, the problem that we have in part is that we have too many options. Every customer will come with their idea. That is technically possible, but we don't really know if that solution is going to work or not. And it's because it's so early and there is so much investment on AI these days, you cannot say no to a customer. So there is a lot of fragmentation out there, and then you get some very sophisticated customers, like on this panel, and some customers that they come, oh, this is just Lego, put it all together. And then you start to put, well, you have signal integrity, power integrity, you need to solve the test problem. And then they go from one side, this is very easy, to the other side, this is impossible, I cannot do this. How can I do mechanical stress simulation on my interposer? And then we need to go, no, Mr. Customer, don't worry, this is part of what the foundry does, you need to work on that. So what we feel is missing is some methodology. Designing a monolithic chip is very, very complicated, but we have tens of thousands of people that they have done it for 20 years. So they feel comfortable doing something very hard. Sometimes putting some chiplets together is less hard, but people don't know where to start. So that methodology that tells people this is how you do it, especially feasibility, right? Should I put 2 chiplets, 3 chiplets, side by side, top? What are the trade-offs? And the tools that we have are very, very good to tell you exactly how it doesn't work. But it doesn't tell you what you need to do yet to make it work, right? So what we need is more feasibility, have tools that introduce some error, but give you guidance on how to go to the end result that you want. I think that that's what's missing. Once that you have a good system partitioning, then it is work. But it is doable, and the products are on the street, they work.
Yeah, thank you, Lluis. So many challenges. You guys have brought up very interesting points from all angles. So we'll get to some of them. But I think for the last topic that you just mentioned,
Yes.
And we've talked about, right, in the design cycle, focusing early on in feasibility and prototyping. So do we think there is enough of a EDA support and capability in this area? What's the guidance from Nitin from a CAD point of view?
Sure. So what I like to say, honestly, even more important than the support as it stands today, is what I like to think of as the level of engagement. Because if we are talking, again, if we're communicating with our foundry partners, with our EDA partners, if we're having those discussions about, hey, here are the products that I want to design, now tell me what my challenges are. Tell me what prototyping feasibility, tell me how I can design this thing, how I can shift left that 3D floor planning process. Then we can guarantee that we're going to be at least thinking ahead toward getting to a better result. Also, prototyping and floor planning, or feasibility especially, is the big new thing. So we did a lot of work on that last year, and the concept of feasibility is not new. And I want to emphasize this because this is a conversation I've had multiple times. The concept of feasibility, especially in a 3D context, is something that architects have actually been doing the whole time. Historically, just maybe 2-3 years ago, it would have been something they were doing on spreadsheets, using back-of-the-envelope calculations. You know, let me just estimate my power distribution here. Let me estimate what my approximate power grid resistance is going to be. Let me estimate what my thermal conductivity is going to be through my metal stack. And when I have that information, I can plug that into some ridiculously complex spreadsheet macros, and then I can start to estimate what sort of IR choke points or what sort of thermal hotspots I'm going to be creating. But what we're starting to see is through these discussions, with foundries and with EDA, we're starting to see a lot of these sophisticated calculations are now getting plugged into our tools. And our EDA solutions, like our 3D floor planning solutions, are starting to show that, hey, I can do that same work using data input, maybe as a spreadsheet, maybe as the 3D blocks that we've started to talk about. And now I can plug those same numbers into the tools, and the tools have those equations now built in, and now I'm getting a 3D GUI, and I'm getting heat maps, an IR heat map, and a thermal heat map, and I'm getting these nice, rich visualizations that I didn't have just a couple years ago. So the tools are getting better and better, and that is what is going to happen as a side effect when you have the engagement. And so that's why I want to say I'm really thrilled that the engagement is there now that we're having those discussions, because the tools will definitely follow, and we're seeing that.
Yeah, thank you.
Yeah, the tools definitely are getting better, and of course, ANSYS is providing a lot of tools, working, also 3D modeling. We've got some CUDA acceleration and physics NEMO models, which is helping thermal modeling a lot. But the biggest challenge still remains. One of the things has been as engineers, are so focused and so on what we know well, and we sometimes don't talk to the neighboring person, and that's what tools tend to do as well, because they do not spread across different domains. They're so narrowly focused. I'm working on thermal. That's all I'm going to solve. How does it impact your SI? Those connections are still to be made better, right? Those are the optimization levels that still remains, because yes, you can put things together. It's just like when we do our chips and we have partitions. Every time there's a boundary, that's where you lose some margins. That's where you lose your PPA. Similarly, when you have boundaries between two chiplets, optimization has to be at the system level, and that's the most efficient system. And that's where the tools probably still lack a little bit, and that's the next level of optimization challenge that we have when we put multiple chiplets from different, maybe possibly different companies. How do we optimize the whole system? How are we saying we are thermally optimal? We have optimal power delivery, we have optimal timing and SI, so everything has to be worked between multiple dies.
Yeah, thank you, Prakhar. So seamless workflows is really coming out as a theme, right? Workflows between people, teams, and products, right? And you mentioned thermal, so let's get into a little more thermal, right? So thermal today is one of the, if not the most important physics thing that needs to be modeled and simulated for 3D IC context. So how are we seeing thermal evolving? Do we have the right capabilities? What are we thinking about thermal management, on-die, off-die? Lluis, you want to?
For us, we see thermal on the multiphysics as the most important, as the core one, that we need to get right. Because there is interaction between mechanical strength, signal integrity on thermal, but thermal is the one that is the key. That's the one that tends to move the other the most, right? So we feel that the thermal simulation, it's in good shape, but it's still not in good shape. As you said, it's putting all together. What is the impact, even as first order approximation? What are the hot spots, what are going to be, what are the likely implications on those, and how could I help my floor plan so that I distribute those hot spots very, very early, even when I don't have RTL, but I have an idea. This chiplet is 100 watts, this one is 20 watts, this is 1,000 watts. There's going to be a gradient there. I don't know how steep, but it's going to be, right? So, yeah, thermal is the number one, and we see EDA, especially ANSYS, following on that direction.
Yeah, thank you, Lluis. So we talked about thermal, we talked about signal, right? All these multiple physics, right? They're all very important. But Prakhar also mentioned the coupling between these physics, right? How important do we think that is? Sonia.
So all these elements, they all depend between each other. There is no way, 3D IC to me is a world of collaboration. Nobody can live in a silo, right? Even when we do technology definition, let's take a TSV. Signal versus power. The TSV for signal, you want low capacitance, right? You're going to have a thinner liner in order to get the best, channel loss, right? But then for power, you want a big, strong copper pillar, right? So which one do you go for, right? It kind of pulls in a different direction.
Yeah.
The same thing, thermal versus power. Where do I put my compute die? You want to put it in the bottom die, in the bottom, next to the package, to power it. But then I need a heat sink, right? So should I put it in the top? Should I put it in the bottom? And I do design technology. The process guys don't know. It's like, okay, you guys wire this part, wire this part. You need to look at both things, and it depends on the system. It depends on the workloads. You have to look at the entire system, right? The same thing, mechanical, warpage, right? The power distribution, you want thick metal. But now we're in 3D IC. The metal stack is even taller. So I want to make, as a designer, thicker metals. The packaging guy said, no, I need to deal with warpage. Cut it, right? In order to reduce power, between different chips, you want to bring integration because most of the power comes between going from chip to chip. So I want to integrate. But then the die becomes too big, then you have yield, and my warpage again is like, I cannot make it happen. And actually, in a panel about 3 years ago, they asked me from EDA if I have one wish, what I would like. I said, I want a magic box that I can put everything in there, my technology, my package, my yield, my cost, the workloads, the system. And to me, the one number big question is partition. What should go to what die, in what technology, what should be the die size, even to do optimization of technology definition. There are so many variables. Right? And it's just, to me, actually, I have fun in 3D IC because it's just, I like to do things that it cannot be done, people think cannot be done. But it's so many variables, and you need to just think too many things at the same time.
Yeah.
So everything is interrelated. You cannot just do one at a time. And it's not just all this multi-physics. You need to think about your design, your technology, but at the same time, the system, the workload. Even if you don't change the software, you probably cannot fully take advantage of the technology. You are leaving woodies on the table.
Yeah, thank you. Thank you, Sonia. Yeah, so we're all working on that magic box as the EDA industry.
I have been waiting 3 years.
Yes.
Magic box is AI, right?
Magic box is AI.
Solve all those problems?
Yeah, there's a lot of progress, and so we need to take into account all these coupled physics early on, from prototyping to feasibility to sign off, and there's a lot of progress in that area. So that was great. So I think multi-physics challenges and the direction how to solve them, that's a great area where we continue to make progress as the EDA industry and as ANSYS. So now maybe let's switch gears to the ecosystem and the market adoption. So as we know, right, and the pictures from what I showed, high performance compute, AI, right, this has been the major initial adoption. So what are we thinking in terms of our other industries, other verticals? Are they catching up? Is it just the big guys working on 3D IC? How about the rest of the semiconductor industry? Nitin?
Yeah. So 3D IC or multi-die, as of today, it's still very big. It's very complex. So when you have this sort of new drive to do something new technologically, you're always going to have some early adopters who are the trailblazers, who are driving everybody forward. And maybe those are the big guys because they have the most capital to spend on it, for whatever reason. But I would say that for every big company that is, blazing this trail for us, you're going to have 5, 10, 15 smaller companies that are watching them, scrutinizing every step they take, every decision they make, and trying to figure out, can we do that? And if we can do that, how can we do it cheaper? How can we do something at our scale with our budgets? How can we be, if not equally effective, but proportionally effective for our market? And the other thing to keep in mind is that, regardless of whether you're that big company, that trailblazer, or whether you're a smaller company, realistically, we're all kind of working with the same foundry partners and the same set of EDA partners. So while yes, you have certain subset of companies that are blazing the trail, we're all, as an industry, we're all kind of learning together. And a lot of that wisdom and experience that is growing out of those trailblazing chips, that is percolating and disseminating through those shared partners, and it'll percolate down to everybody else. And over time, of course, another thing that you'll see is, of course, a lot of these processes will become commoditized with time. a lot of your products, a lot of your chiplets, a lot of your HBM memory, whatever it is, will become more commoditized, more generic. You start to see interface standards like HBM, UCIe. You start to see 3D blocks as a design standard. As all of these come together and start to streamline the process, those costs are going to come down, and they're going to keep coming down. And over time, eventually, it's going to become just fair game for anyone. We're all going to find ways, maybe for the smaller companies, I'm going to focus my in-house design teams on my core differentiating logic, and this more generic functionality I can just start to buy from that chiplet marketplace. And so with time, you start to see this just commoditization and just after a while, it'll just become a free-for-all where the money is there because everything has just become less expensive and more optimized, and then so it'll just be a free-for-all for the whole industry. And we can all together move forward and all just start playing in the space.
So the trailblazers are blazing the trail, and this collective knowledge is increasing and improving. That's going to help the rest of the industry going forward. And one of the things you mentioned, right, that's going to help with all of this complexity is standards, right? You mentioned some of the standards.
Absolutely.
3D blocks, right,
Yes.
is another standard that was pioneered by TSMC. So where are we going with?
So what we believe is some things are common to the whole industry, and trying to differentiate on that, it harms the growth instead of helps. So TSMC and ANSYS and Intel and several others got together to define a syntax for chiplet. Basically, you could call it left-def for chiplets or Verilog for chiplets. It doesn't really matter if it is a colon or a semicolon, or uppercase, lowercase, something common that all the tools read, because everybody has a mixed flow of tools, and customers can go to silicon as soon as possible. Of course, being a foundry, we saw that, we are not an EDA company. We are not qualified to be an EDA company, but we saw the lack of standards being an obstacle to the growth of the chiplets. We see below 5 nanometers, more than 90% of the tape outs are chiplet-based. But people cannot even describe the chiplet into the tool. So we needed, it got to a point that the same EDA company had different formats. So that's something that everybody has benefited. Now, is everything going to be standards, public standards for everything? Probably not, right? There are things we support 3D blocks, which I think helps the whole industry. We are not licensing our COAs, we're keeping that to ourselves. So as always, there is going to be a mix of things proprietary, but you differentiate because it's your own technology, and things that sharing benefits lifts all the boats, including ours.
Yeah.
That's how we see it.
Yeah, exactly. Yeah, and now it's donated to IEEE.
So now it moved into IEEE. So all of you, if you are an entity of IEEE, are welcome to join. It is moving fairly well. Interesting discussions on how you can make it even better. More generic cases. For instance, on 3D blocks, we have all the rotations 90 degrees. Some people came, hey, I'm doing my chiplet benefits if I can put 45 degrees. It was not supported on the language yesterday. Yeah. It's going to be supported tomorrow. That's an example of bringing system customers into the standard, making the standard better for everyone.
Yeah, thank you. And Nitin mentioned, this is also going to enable going forward, right? Multiple chiplets coming together, maybe going towards a chiplet marketplace type environment. Today, AI accelerators with HBMs, right? The base die, GPU, interposers are coming from different vendors. That's a good example, I think, on that track. So Sonia, so what are you thinking in terms of, are there potential? Are we going towards this kind of a chiplet marketplace? What would be the chiplets that you want to see in that marketplace?
So to me, chiplets is the next stage. At some point, we talk about SoCs, right? Everything was a Lego pieces. Can we put it together? But to me, in order to chiplet to work, you have to have a clean interface. So if the partition is defined that this is my IP, this is my compute die, right? Maybe we can have these Lego pieces on one more level. But it requires, like Lluis said, standards. Who's going to own the certification? No, there is a concept even like, should it be a hard IP or a soft IP? At what point, you want to have maybe, like when we do foundation IP, the memories go to certain metal layers. Should the chiplet be hardened to certain level and then from there take it to a foundry where you can optimize it across dies? Or should it be a soft IP, right? Now, how are you gonna do data sheets? What are the metrics? Should I measure it from the output of my functional block? Now, if I have a interface, UCIe or even a HBI buffer, right? It doesn't add to the logic. It's just a communication. So from where to where I should measure, we need some agreements again, how are you gonna measure that? Now, in my opinion, when you go to 3D hybrid bonding, that's a different world. Because the top and bottom die are like married together, right? Yes. You are co-optimized, right? So you cannot say, I'm gonna buy my compute die and glue my L2 cache at the bottom kind of thing, right? So I think that's a different world. So I do believe, like, for SoC, we made it happen. We can, it's a good way to go. And it will help, actually, if it's something that you're trying to do a prototype, like let's say FPGA, and you can get chiplets, you can actually get it to the market without having to wait for too many things. But it won't fully be performance optimized. So you can do an early prototyping of certain systems also.
Yeah. Mm-hmm. I'll echo what I said earlier, right? Like NVIDIA did, we have the NVLink Fusion, which allows other vendors to be able to make AI systems better, or have access to the systems. And those kind of technologies, because again, this is an ecosystem problem. Nobody's going to succeed alone. We have to have partners. We have to have standards are a way to get there. They're just side effects, because we realize that when we work with, it's just this communication problem again, but this is between companies, between multiple companies. How do you communicate your requirements, and how do you know the other person understood what you're asking them? But ultimately, this again opens up collaboration. It opens up multiple companies who are expert in their own domain to be able to put together a product which is higher and better than any one of them could have done by themselves. And that's really the opportunity that we have right now. And we keep thinking in terms of, we used to think of small systems. And again, there are applications where, a small chip is sufficient. But compute in general is growing. Compute is where there's nobody who says, we are done, we don't need any more compute. We'll obviously need a lot more compute as we go. And the way forward is to integrate and make bigger systems, and to do that, you have to always put multiple chiplets is one way what we see today. I mean, of course, future technologies will have even better ways of putting things together. But in the next few years, we have the way to make better systems is to collaborate and to be able to have standards to be able to solve these multi-physics problems, so that we can create new things which we never could dream of like 5 years ago.
Yeah, exactly. So great. So it's a very good potential in that direction.
Yeah.
Yeah, please.
Yes, on the chiplet, from the foundry point of view, on the chiplet marketplace, we feel that there is a disconnect between wishes and reality, right? We hear customers, well, I just hope that someone is going to spend $300 million to do a chiplet that they will sell to me almost for free. That's not going to happen, right? So the reality, what happens is more than 95% of the chiplets that we see are proprietary. People take one design that is bigger than it makes sense to a monolithic die, and they split it in multiple ones, with the exception of HBM. So it is rare still to have an independent chiplet that is generic enough to work with many solutions. It is possible. But the business case is not trivial. And the people that are in best position to do that, like IP companies, they are very careful. Their business case is not about having hundreds of millions of dollars on the nitrogen chamber, right? They want to sell soft IP,
Right.
GDS2.
Right.
So I think that is going to be a standard chiplets for things like I/O chiplets, with UC Express and PCI, there are cases like that. But the idea that is going to be, I don't know, I need PCI, I will get a PCI chiplet. Does anyone sell a PCI chip? No, right? So just because you remove the plastic is viable? No, it still is not viable, right? So I think that the industry needs to move ahead. Okay, there is the wish space, this is reality space. How do we make the reality space bigger, because otherwise we're not breaching, right? And this is just to try to bring questions for you guys, to keep you awake on the afternoon of the second day.
Yeah, those are great points. So the conversation will continue, right? There's pros and cons and the feasibility, the practicality, I guess, of the final solution. So talking more about maybe foundries and OSATs, right? Do we think the role of foundries and OSATs, are they changing? Are they getting closer to designers, right? We're seeing foundries and OSATs standing up, design teams, pathfinding teams to really maybe start focusing on more of the multi-physics effects.
Okay, so
Go ahead.
You're the right person for that.
Yeah.
So what has fundamentally happened is that in order to get the bandwidth between the chiplets, we needed to have silicon interposers, right? And the silicon interposer is basically you need silicon equipment. So by definition, you got to the point that foundries needed to do it. Intel needed to do it, TSMC needed to do it. There is also a business issue is that we enjoy significant profit margin that allow us to invest. The OSAT market by nature is low margin, so it's difficult for an OSAT with a low margin to be able to do the capital spending to come with new technology. So that's why it has been foundries that have been pushing the advanced packaging, the hybrid bonding at the end. Now, as you said before, some of those technologies are going to be commoditized. I expect some of those technologies will be licensed to the OSATs once the R&D is done, and the foundries will go to do the even more complex, even more valuable package. So what we expect to see is the OSATs starting to participate through licensing, doing assembly, which is easier, but not having the silicon tools at the beginning.
Yeah, and actually that is a complication that you see is the foundries are very experienced, and especially when it comes to, again, for me as a CAD person, I think a lot about, okay, well, I'm using this tool, I need this PDK, and I know that my foundry is going to deliver that PDK. And as OSATs start to get into that space, we're seeing that some of them are going to need to do a little bit of learning to start thinking about EDA tools in the same way that foundries think about it, in the same way that design companies think about it, which means you need to start to see PDKs maybe from the OSAT, and that's probably a new bit of learning that's going to have to develop.
Yeah, focusing more on the assembly. Yeah. Okay, yeah, great points. So one thing we haven't talked about yet is co-packaged optics, right, which is also now becoming more prevalent. We've heard from the recent NVIDIA announcement. There's significant investment and roadmap in this area. Maybe Prakhar, you can share some insights on that topic.
Yeah, so this brings up the fact that we are going to create these chiplet-based designs for a use case. We are not just doing it because we can do it, right? It's like, oh, I can do this, I'm going to do it. That's not the point. The point is the end goal. So when we see a bandwidth bottleneck, for example, or we have to say, okay, we have to build systems where the data does need to be transferred for a longer distance, and optics is the way to do it. So those are the use cases which it unlocks, which we couldn't think of in the past. Now it's unlocking those use cases, and everybody is going back and thinking, oh, this is a real option that I have to solve a problem which was unsolvable in the past. We couldn't think about building a massive GPU, like a whole rack which looks like one GPU. But some of the advances allows us to build something like that. And co-optics is exactly that. It's one of the tools in our toolkit, and it just allows us to build newer kinds of solutions for the world.
Yeah, thank you. So another, I think we've almost covered an hour, and we haven't really talked about AI, except the magic box, right? That might be AI. So where do we think? So how do you think EDA companies today are utilizing AI, and what are the possibilities? What can we work on further in this area?
Well, the funny thing about AI is it's becoming the big buzzword, obviously, and we're all trying to look at it more and more. And we start to have more of these conversations where it's like, well, do I need AI? Is it the luxury of let me keep doing things the way I'm doing it, but on the side I'll start to play with AI a little bit. And what we're seeing realistically going into the future is that it's not really so much a nice to have as an absolute necessity going forward, especially in the realm of multi-die. You start to think about, I'll give a couple examples. some of the things that I've started to started to think about. Let's say you have your multi-die product, you have your HBM and your SoC talking to each other through a 2.5D interposer channel. And my design team, my architect has come to me and said, okay, the channel interaction for this HBM interface, you need to go, here's your data rate. It needs to be some gigabits per second number, and you need to be performing at that spec. Well, I know what the metal stack is in my interposer. I know I have so many metal layers. I know I have some options in terms of pitch, width, spacing. I have shielding, different shielding possibilities for my ground shielding, whatever, you know. I need to figure out how I'm going to implement those channels, that routing. I can't just route it one way, see if it's good, route it another way, see if it's good. What I need is some kind of just open exploration of the design space. And so what we're starting to see is, in the AI space, is tools that can, you give it the parameters of, here's the thing I'm trying to route, here's some parameters that you can play with, and just go have fun. And what you're seeing is this tool can now kick off a series of experiments in parallel, you know, try 10 different iterations with different spacing, different shielding, et cetera, and then run some, I have to worry about my SI metrics, I have to worry about my route length, I have to worry about resistance, insertion loss, return loss, near-end crosstalk, far-end crosstalk. These terms are being drilled into my head every single day now when I have these sorts of discussions. And so now these tools can do the routing experiments, run these SI metrics automatically, scoreboard my different routes, tell me which one scored the best, and then, oh no, I'm not done. I'm going to do another 10 experiments. I'm going to double click on whichever one did the best and do another 10 which are just slight variations of that one that did the best. And after 2 or 3 iterations, I have finished in maybe a day and a half, maybe 2 days. I have done what would have taken weeks or months to do manually.
Right.
And so you now see this ability for an AI-driven solution to go just explore a design space. Another great example is bump planning. You know, we have these huge chiplets and these huge dies, and these things have thousands of bumps, tens of thousands of bumps, and you're going to put out 20 or 30 of these things on a giant interposer, and they're all going to talk to each other. And I need to bump plan this thing in such a way that these bumps that are talking to this chiplet are optimized here, and these bumps that are talking to this chiplet are, and it's thousands of bumps. I can't do this manually. I need automation in this space. And again, you have this proliferation of new tools that are applying AI to just explore the space and just try different solutions and then figure out what is the optimal solution in all these different problems. And I think as our ambitions continue to grow bigger and bigger, this is not something we have the luxury of treating as a nice to have. It's something we really need to explore as a necessity.
Right, right. Yeah, that's a very practical and high value application, I think. I agree 100%. So instead of doing manual millions of simulations, smart sampling, creating a machine learning based meta model, then explore and optimize.
I think even if you find a solution, it might not be the best solution, but there are so many variables. Even when we do technology definition, we run sensitivity analysis, but everything is interacting between each other, right?
Yep.
So it's like, you need AI to figure out what is the best optimization, even for technology. And even when I go to the design spec, you might be able to construct something, but it might not be the best optimized solution to really squeeze the best out of it.
Yeah, that's really a great application, design space exploration.
Yeah, when we think of AI, I think AI is now used as a big umbrella word which covers lots of things. Personally, my passion is to get GPUs to accelerate our workloads. Technically not AI, because a lot of things when we think about an AI right now is some kind of intelligence coming back. We're not asking it to act its intelligence. We have the intelligence. We're just asking it to run multiple things and provide us sort out through that and give us a solution, right? Sometimes people get too bogged down by what is this AI, how am I going to use it? But one thing we earlier touched upon, the biggest challenge is communication. And AI could be an amazing tool in communication. Everything that Nitin talked about, he goes to a meeting, he can't explain it because he's got so much in his head and so much depth and understanding, right? You go talk to a different team and like, what are you talking about? And with using AI, he can very quickly draw out pictures, he can use visuals, and he can communicate his ideas so quickly. And that's just the power of it. That's like collaboration tool. It's a tool which even helps you think sometimes, and that's the real power. Of course, EDA, that's the normal thing people think of, like, okay, I'm going to run everything faster. Of course you are going to run. That's a given. But how else can we use it? It's collaboration.
It's a great example.
Yeah, another great example.
Yeah.
All right, well, thank you. Yeah, please, Luis.
Yes, on AI, our experience is similar to what we have heard from the others. So the only thing that the AI is not good at is kind of sign off. For everybody else, for exploration is great. Yeah. And so what we see the trend is more and more, especially parallel algorithms like DRC, LBS, they're going to be moving into GPUs. So we're going to create this virtuous cycle on which we improve the tools to run on GPUs, allow us to generate better GPUs, better systems. That is, even in Moore's law, it slows down. Well, maybe AI help us to keep growing, right?
Yeah.
To keep expanding.
Yeah, until everything becomes fully autonomous and Cylons and nobody's needed, but that's hopefully another 50 years.
We'll be retired by then.
Right. Okay. Yes. And we had I guess we can talk about this for at least another hour. But yeah, we are out of time. Many questions I had. We didn't have time to talk about. But yeah, thank you everyone. I think this was a really great discussion. We covered many topics, and this is really a very exciting topic. Very fast pace of innovation across the ecosystem, and it's really a great opportunity for everyone here, I think, right, to be a part of this as part of our industry going forward. So we do have, I think, 4 or 5 minutes. If any questions from the audience.
We have 2 microphones in the aisles if you'd like to ask questions.
Did we solve all problems and questions and challenges?
There is one there.
As long as you throw AI, then all problems automatically get solved.
So you talk about the 3D blocks for open format.
We don't hear it. It's not working.
3 blocks.
And
3D
Arturo,
blocks.
if you can please introduce
All right.
who you are, where you're from.
Yeah, Arturo Demircan from NXP. We talked about 3D blocks.
Yes.
So that's a new format. So we're trying to. Is this going to be covering all? All the foundries, all the EDA companies? Are you trying to make it a global technology introduction?
That is the intent. Yeah.
Sure. So yeah, 3D blocks, the plan is to be an IEEE standard to support any foundry, any technology, doesn't even need to be silicon, from all EDA tools, commercial EDA tools, academic EDA tools. It is a syntax to define the geometry and the connectivity of chiplets. So any foundry, any vendor is supported.
Are there other companies that you're working with, like CDX? Also, it was also mentioned some circles. So are you planning to work together with them, or is it going to be going in different directions?
So if I hear the question correctly, is how can you engage?
CDX is a different syntax, maybe the alternative format that might be going in parallel. Are you planning to work with them, or are you trying to coordinate so that they will converge at some point?
Where is CDX from? I haven't heard.
It's so from other companies like I think Siemens is
not
also
from a foundry.
Not foundry is also a part of that.
Okay.
You may want to discuss later, perhaps.
Okay, sure.
So what I can say about that is 3D blocks is an industry standard. Everybody is welcome to join and to bring feedback. We expect that 3D blocks will be improved. We expect that some of the, for instance, there is a discussion to improve the BAMP map with something from JEDEC. So if there is something, a better way of doing it, it is welcome. It is not something that any of us control anymore. It is a work group, right? So it doesn't matter if I think something is great and the work group votes against it, it's not in. And if the other way around, if I don't like it and people work in favor, it's on the standard. So.
And it's
I'll follow up with you guys.
continuously evolving standard. So it started at 1.0, then 2.0, then 2.1.
Right, exactly.
And so it's something that I've been working with for multiple years now. And so it's something that when I've worked with it, I've very greatly appreciated. Like we talked about feasibility, that was part of 2.0, 2.1. So yeah, so I'm a big fan of 3D blocks. I've used it in multiple roles and multiple products, and I definitely greatly support it.
It will continue to evolve based on feedback from semiconductor companies and EDA, as it has so far. Okay. Any other Questions, comments? All right, so I guess that's it. So thank you, everyone, for attending.
Thank you.
Yeah, thank you, everyone.
Thank you.
Thank you, panelists.
Thank you for joining us here at the Exhibitor Forum today. Please join us tomorrow for the last 4 sessions, starting at 10:30. And we will have 4 more sessions tomorrow, starting at 10:30.